So, we will now try to find what are the conditions for incompressibility or conditions for solenoidal velocity field. We can say solenoidality of velocity field. They are anonymous, they are synonymous. Whether the flow is incompressible, for only in incompressible flow the complete velocity field is solenoidal. If the flow is not compressible, then also it has a contribution which is solenoidal contribution, but the complete flow field is not solenoidal. Only when the flow is incompressible, the complete velocity field is solenoidal. Okay. Now, what is the condition for incompressibility? We have already seen the flow is incompressible if divergence of u is 0. Okay. So, incompressible if now, what is first of all, see we will compare here again the order of magnitude. What, because these are basically approximation, that we know that what we are doing are basically approximating, it is not an exact condition. There is no fluid which is exactly incompressible. Okay. So, this is never exactly true, but approximately true. Under what condition we can think that this is approximately true. Okay. That is what is always approximation means, that under what condition this is approximately correct. If there were an exact incompressible fluid, then we would have got exactly divergence of u equal to 0, but since no fluid is exactly incompressible, we are not expected to get divergence of u equal to 0 exactly. So, we are likely to get it approximately. So, approximation means under when we can treat it 0 or when we can neglect it. Now, what is the order of divergence of u? Once again let us consider that we have a characteristic velocity scale which is u infinity, characteristic velocity is u infinity, characteristic length is L. So, reference, or you can say reference quantity. Once again we call it u infinity, and similarly the length we call it L. And we will see that we will think divergence of u equal to 0 is satisfied if divergence of u is much smaller than u by L. Divergence has the order of u infinity by L. Okay. Each of the term has the order of magnitude as u infinity by L, du dx plus dv dy plus dw dz, each of them is having the order of magnitude of u infinity by L. So, we will call that divergence of u equal to 0 is satisfied if divergence of u is much smaller than u infinity by L. So, we will sort for this. If we find some condition at which this divergence of U infinity is much smaller than U infinity by L, we will take that okay, divergence of U equal to 0 is satisfied. Now, what is divergence of U? We have seen that that is the rate of dilatation or rate of expansion. So, divergence of U we can replace by this term that is the continuity equation, is not it? D rho dt plus rho divergence of U equal to 0. So, divergence of U equal to 0 means that d rho dt or 1 by rho d rho dt equal to 0, because our original continuity equation is this comes from the continuity equation d rho dt plus rho divergence of U equal to 0. These equations you should remember, particularly this continuity equation, moment and Navier-Stokes equations or momentum equations, Euler's equation. So, divergence of U equal to 0 means 1 by rho d rho dt is 0, or divergence of U is much smaller than U infinity by L means 1 by rho d rho dt is much smaller than N. This d rho dt now we would like to express in terms of pressure. To do that, let us see that what we have dp dt. What is dp dt? dp d rho but pressure is in general is a function of, pressure is a state variable and in general is a function of another two state variables. Assuming that the fluid is a pure substance, then pressure is or any state variable is function of another two state variables. So, assuming that the pressure is the function of density and say entropy, we know that these can be written in terms of this, perhaps you have written capital D, you can make it capital D also. Then this is at constant entropy, and again it will be sorry. This dp d rho at constant entropy is called the acoustic speed in that fluid, speed of sound in that fluid, the fluid which you are considering, and usually denoted by C. If it is air, then okay, it is speed of sound in air. If it is water, then it is speed of water, sound in water. Okay. So, we see the condition for solenoidality, this is now become this. So, the condition of solenoidality has now become that 1 by rho d rho dt, that becomes 1 by rho c square and now then we can write it as two conditions. Now we can write it as two conditions. Sorry. This has to be less than u infinity by L, that implies that each of these individually must be less than this. So, what we stated so simply that if the change in pressure is very small, then we can consider the change in density is negligible. Instead of that, we have come these two complex conditions, 1 by rho c square dp dt is much less than u infinity by L, and even more complex 1 by rho c square dp ds at constant entropy, sorry, constant density, and then rate of change of entropy. Now, let us see what each of these term implies or each of these mean. For that, let us try to find what is dp dt. What is dp dt? Let us get it from equation of motion. We have to find what is this first term dp dt. dp dt you can write in what way? 1 by, should we put it, okay, we will put it that later on, 1 by rho c square dp dt. dp dt is this. Okay. And considering that this equation rho u du dt. A scalar product of the velocity vector with the Euler's equation. Euler equation scalar multiplied by u. This is Euler's equation scalar multiplied by u. From here you see this we can replace, this term we can replace from here, this is here. Okay. So, what we had this or can you see it? One, the first term one by that q square is as before the scalar product of u. So, this will be satisfied if each of these terms are individually less than u infinity L. Okay. Remember, this is not the complete conditions. We have already split the condition into 2 and that one of those 2 is split into further 3, or meaning of that is these 3. If all these conditions are satisfied, okay, then okay, they are not the only, there will be more. So, these are the required conditions, some of the conditions which must be satisfied, so that the flow can be treated as incompressible or the velocity field can be treated as completely solenoidal. Now, let us see each of these, what do they mean. What you can say about the first term, what will be its order? What will be its order? Or should we start with this last term? Okay. Last term will perhaps be simpler. Last term will perhaps be simpler. See, what will be the order of this term? What will be the order of this term dq square dt? So, let us first consider the third term. Yes. Okay, of course, we will consider all, but let us start with the third term. Third term contains dq square dt. We are interested in the order. What will be the order of magnitude of this term? That is all. This, as you know, by definition is this. So, its order can be obtained either from here or from here, any of the term. So, what will be the order? The velocity is of the order of u infinity, the length is of the order of L. So, time is of the order of L by u infinity. So, its order is, yes, order is let us say this diverge, this is some gradient operator of q square. So, that is u infinity square by L, this term, this another u infinity. So, it is u infinity cube by L. If you look here, it is again u infinity square by L by u infinity, again u infinity cube by L. So, this term's order is u infinity cube by L. Okay. Of course, this term has a multiplicating factor 1 by 2 c square. 2 of course has no significance. Then what is this means? If we say u infinity, let us keep c as c. C of course, you can express in terms of some order, but let us not worry about it. This is some parameter. So, the third term implies that the order of it is order of u infinity by L. Sorry, oh, much less than, sorry, not nearly, this is much less than u infinity by L. So, what does it implies? So, what this condition says? So, this okay. So, this is the condition, the first, I mean one of the condition, but in particular think about a flow in which this body force has not much of influence and the flow itself is steady, there is no time change. So, look, out of these three, if the body force has no significance, I mean not much of significance, this term is practically we need not consider, body force is not present or body force is insignificant, meaning that we need not even worry about this term. If the problem is steady problem, this term also have no meaning. This is present only if unsteady also. This is present, that is the first of the condition. The first of the condition is only valid when there is some unsteadiness, time dependence. If there is no time dependence, everything is remaining independent of time, then of course this is not of any concern. And in particularly the other conditions which we have left here, that the condition related to entropy, if this is totally negligible in that type of situation where the body force is insignificant, where the problem is steady and where this change in entropy is again not considerable or negligible, or the flow is isentropic. In that situation, you see this is the perhaps only condition or most important condition. And what is the meaning of this term? That okay, if this condition is satisfied, then because it has come from the first condition, the first condition says about rate of change of time. This is significance of this condition. Okay. This is an outcome of this term, which is fractional rate of change of pressure. So, what it means then, that when body forces are insignificant, the flow problem is steady, the entropy changes are also negligible, then all pressure changes are basically related to this term. And if this term is very small, this U infinity square by c square, if this parameter is very small, then the pressure changes are also very small. What is this U infinity by c square? This is a parameter commonly known as Mach number. So, a very important condition, and as you see, perhaps the most important condition, the flow field to be incompressible or solenoidal, because that most often you will find the problem is really steady problem, and particularly in aerodynamical problem the gravitational forces are often negligible. Also in many practical problems the gravitational forces are practically insignificant. It is not that the force is very small, its changes is small, because most often we are interested in change, not exactly the total amount of that quantity, how much it is changing. So, think about in many flow the change in gravitational energy is practically small, because the change in gravitational force will be considerable if the change in altitude is quite high, otherwise not. Just about a few centimeter or even a meter or couple of meters difference in altitude hardly affects the gravitational force. Gravitational force will be of the order of other forces, or change in gravitational forces will be of the order of change in other forces only if we are considering an altitude which is quite large. So, except perhaps in atmospheric flow, in most cases the gravitational effects have not much of contribution. Anyway, so this is one of the condition Mach number, and we will see that quite often people answer that okay, what is incompressible flow? Okay, incompressible flows are those flows for which Mach number is less than 0.3, that you will see a common answer. Though of course, answer is completely wrong, but the source is here. The Mach number is perhaps the most important parameter which decides whether we should treat the flow as incompressible or not. Okay. So, what you see that one of the important or the most important condition when the flow can be treated as incompressible or the velocity complete velocity field is solenoidal is whether the Mach number is small or not. Okay. If the Mach number is very small, we can. Let us now consider the second condition or okay, or come back to the first term due to importance. Okay, what will be the order of this term? Think about an unsteady flow. Now, we have already considered a characteristic length and characteristic velocity, but here we need even to consider a characteristic time. Now, in a general unsteady phenomena, the change is of course not a simple periodic change. In a general unsteady phenomena, the change is not simply periodic change in time. A general case, there will be a combination of many frequencies, not just one or two. And let us say that of course, we cannot take all those frequencies to be as the characteristic frequency, but we have to take the characteristic frequency. Let us say the most fundamental or the most dominant frequency we take as the characteristic frequency, and hence its inverse as the time, characteristic time. So, let us consider the characteristic frequency to be n and its characteristic time is then 1 by n. Now, we have also characteristic length L and characteristic velocity u. So, what will be this term then dp dt, the order? What is pressure? What is pressure? See, it is again related to change in momentum. Pressure is simply change in momentum. So, to find what is this pressure term, what essentially you have to find out what will be the order of momentum change or over this characteristic length L. Perhaps you have studied a kinetic theory of gases, where you have first found out how to find the pressure by simply considering the momentum as the molecules collide with the containing box, that gives the pressure. Eventually, that is what is pressure is in thermodynamical sense, is simply rate of change of momentum due to those collisions. So, now what we are interested in, what will be the change in momentum over this characteristic length L. Yes, we have U L N. Or you are talking about the entire term? No, I am not going to entire term. First of all, let us see what will be that order of the pressure. Order of the pressure, then order of this time derivative of pressure. Pressure will be of the order of since the order of the frequency is n. So, n times this change in momentum will occur no, n time, that is why this rho u will, and then this dp dt is n. N is frequency, as you said, that characteristic frequency. Frequency of oscillation is changing with time, no, unsteady flow. Sure. How many times it is occurring this assuming that okay, this L there is a box and the particle. So, n times will that particle, some particle will hit over that. So, we have now u infinity writing now. And this then can be written as n square L square this will happen if it is n square L square by sometime it is also written in this fashion. Remember this number, this non-dimensional parameter n L by u infinity. We found this when we non-dimensionalized this equation and call this Stokes number denoted by St, Stokes number in the last class. So, this can also be written as and of course, as you see that this condition is required only if the flow is unsteady. If the flow is not unsteady flow, if the flow is a steady flow, of course, we do not need to check whether this condition is satisfied or not, they are automatically satisfied, there is no change in time. So, for an unsteady flow, then both these conditions must be satisfied, the earlier condition as well as this condition. And you see, in that situation this condition is even more stringent. It may be possible that the Mach number condition is satisfied, that Mach number is very small, but even then this may not be satisfied. Just look to the situation, if the frequency is of the order of or larger than u infinity by L, it can quite often happen, the frequency is larger than u infinity by L, then u infinity by c square is satisfied much less than 1, but here it will not be satisfied. So, if the frequency of the dominant frequency or the characteristic frequency is larger than u infinity by L, this condition is more restrictive than the other one. So, even when the speed is very small, the flow Mach number is very small, but if something is oscillating at a very high frequency, very large frequency, then the flow resulting flow need to be considered as compressible and divergence of u equal to 0 will not be satisfied. The other condition that remains, I think that was that we wrote in between, the second in our writing, yeah, it was that second u dot f. Of course, further we can say anything if we know what is the nature of this body force F. So, consider this F to be only gravitational, oh, c square. Then what is the meaning of this condition? What it says? What? I couldn't hear. No, but see, this is gives that under what condition this will be, this term is small or this term is negligible. If this is the body gravitational body force only, then this is G u c square is much less than u infinity by L. What does it mean then? Remember, see, this is not what we have, what we want to have. We want to have this condition. Okay. We want to have that this must be smaller than this. It is not that it is by default this is like this. We want or we would like to see when this will be smaller than this. This is what is required. This is what is not automatic. We would like to see whether this is going to happen or not, and if it is going to happen, then when. So, this will be satisfied or the condition will hold if G u infinity by c square less than u infinity will be less than u infinity by L if G L by c square is much less than 1. We wrote something G L by c square, G L by that was G L by u infinity square. This also can be written like this, G L by u infinity square, again u infinity square by c square is much less than 1, or u infinity square by c square is m square, and if you remember that G L by u infinity square we defined as Freud number. Anyway, let us try to see little more of this term G L by c square. For c square, let us consider an isentropic situation. Considering an isentropic case, c square is gamma p by rho. The speed of square of the speed of sound is gamma p by rho. So, for isentropic flow, G L by C square is rho G L by gamma p. Okay. And this has to be less than 1. Now, rho G L we know is the difference between the static pressure at between 2 points with a distance of L. Okay. Altitude of L, this distance is of course in the direction of G, vertical direction. So, if the difference between the two altitude or altitude of 2 points is L, then this term actually represents the ratio of this hydrostatic pressure and this pressure. So, you see this, okay, the gamma we can forget, gamma is of the order of 1, gamma is of the order of 1. So, gamma has no contribution. If rho G L by P, now P let us say consider air, where P is the atmospheric pressure, which is again of the order of 10 to the power 5 Pascal. So, this will be of the order of 1 if rho G L is also of the order of 10 to the power 5 only then. If it is not, if it is much smaller than that, then of course, this term is satisfied, this condition is satisfied. So, as long as the altitude or the difference in altitude between the 2 points is not considerable, which is equal to this about p, that means when the altitude difference in altitude of the order of p by rho g, only then this term will become important. So, if L is of the order of p by rho g, only then it is this term or this condition is important, otherwise it is. So, for air it needs about something 8 kilometers. So, if we are considering a distance of 8 kilometers between 2 points, then we have to think about this term and we will see whether the condition of incompressibility will not be valid. But see, most often we are not interested in an altitude of the order of 8 kilometer for any particular problem. We do not want to see what is happening over 8 kilometer of the atmosphere. So, usually this condition is by default automatically satisfied, at least for all practical aerodynamical problem or even any industrial fluid dynamical problem. This condition is, however, if you are interested in meteorological problem, would like to think about the climates, weathers, then of course, we need to consider about 8 kilometer and we cannot neglect the effect of this term, and since this term is considerable, we cannot consider the equation also to be incompressible. Then we have to consider compressible equation. But if you are not, this condition is automatically satisfied. Not to hold the condition. So, you see that out of these three, this condition we can say more or less always satisfied for all practical problem. We need not bother as far as the effect of Froude number is concerned or effect of the body force is concerned towards compressibility. Effect of body force towards compressibility is not considerable unless we are interested in a very large height of the order of few kilometers. So, that condition we can say always satisfied. So, in any problem we have to just check the other two condition, or the Mach number is considerably less than 1, and if the problem is unsteady, look to that. Of course, we have one more condition still unexplored, that is related to entropy, but we will just mention it later, perhaps no time today. But you will see that that condition is also almost always satisfied for all practical problem, unless you are considering very small size. The second condition relating to that entropy and all, that part will come only when you are considering very small size or something like that, otherwise that is automatically satisfied. So, you see that what will happen, that flow field will be treated as incompressible or velocity field solenoidal if the Mach number satisfies the condition that the square of Mach number is much smaller than 1 or Mach number is very small, and in case the problem is unsteady, then we are more important that n square L square by c square is much less than 1. However, if the problem is not unsteady, that condition is also not important, and only the condition of Mach number remains. So, you see that ultimately we have come down to that only the condition of Mach number is important to determine whether the flow is incompressible or not. But for steady flow, for unsteady flow the other condition is even more important, that n square L square by c square. But for steady flow this is the condition Mach number, and that is the reason people often just take it as a thumb rule. If the Mach number is less 0.2, 0.3, then flow is incompressible.